Yeah, so welcome to my talk about the Fujisaki-Okamoto transformation and certain implementation choices from a provable security perspective. So I know the title is a mouthful exactly in the morning, but bear with me. Okay, so when we're talking about the Fujisaki-Okamoto transformation, we are talking about key encapsulation mechanisms, which is one of the two things NIST aimed to standardize during the post-quantum competition. And essentially, it's like a public key encryption scheme, but instead of sending over an encrypted message, you send over a secured symmetric key that you can then use to do fancy stuff with symmetric crypto. And if we look at the NIST competition, all of the proposals essentially follow the same approach. You pick your favorite computational problem, maybe learning with errors, might be Entropy, might be syndrome decoding. Then you use this assumption to build a public key encryption scheme, and then you push it through the Fujisaki-Okamoto transformation, or short FO. I will say FO a lot, probably. So FO is a generic recipe that turns public key encryption into a key encapsulation mechanism. And when FO was originally designed, people, I guess, didn't yet have post-quantum security in mind. So the original proofs did not consider that public key encryption schemes could sometimes fail to decrypt, like lattice or code-based schemes. And the proofs also didn't account for quantum attacks. So this is why in 2017, a paper came out that captured both of these aspects. And there has been a lot of follow-up work since then, because originally the quantum proof only worked for a somewhat unnatural variant of FO. I'll be talking about this in a few slides. And also the security bounds we devised were quite suboptimal because they were highly non-tight, meaning they only apply to way less efficient schemes. Okay, so to contextualize this paper, let's quickly recap what we know about FO so far. So the initial idea is pleasantly simple: to establish a symmetric key between Alice and Bob. Alice can just pick a random message, encrypt it, send the encryption over to Bob, and then they can derive the symmetric key by pushing the message through a hash function. And if you model that hash function as a random oracle, then it's quite reasonable to argue that the key should be that as an attacker, you cannot learn too much about the key unless you're able to break the encryption scheme. However, plain key indistinguishability is not what we aim for during the NIST competition, and also not something that's sufficient if we want to plug this key encapsulation mechanism into bigger protocols. What we actually need is security of the key, even if an attacker could request decapsulations of ciphertexts of its own choosing. This is called NCCA security. So we need to do a little bit more work. And FO deals with this advanced setting by altering decapsulation in a way such that adversarial decapsulation queries are either useless or forbidden. And the way how it does that is that it alters the decapsulation procedure done by Bob. So Bob will only set the key to be the hash value of the message if the decrypted ciphertext, so the plain text, will survive a certain sanity check. In the literature, this is often called re-encryption check. And if the message does not survive the sanity check, Bob will reject. And this can mean two different things. There are two alternative approaches to how we reject invalid ciphertexts. And as of today, it's still subject to debate which variant would be better to pick. So the first variant would be to return an explicit failure symbol. This is what we usually call explicit rejection. And the alternative approach would be to derive the key in a pseudo-random way from the ciphertext. So we get something that's still in the key space. And since this somewhat hides that we rejected, this is often called implicit rejection. Sorry. So if we think about which variant to pick, there are two separate multiple ways to look at it. The first one would be the practical intuition. Practical intuition, you could say, if you do implicit rejection, you essentially hide from the attacker that you ran into the rejection branch. So this might add a layer of security. But then people who think about how these key encapsulation mechanisms are used in practice might counter that often these schemes will be used for an initial key agreement. Afterwards, people are doing some additional, oh, yeah, thank you, right. People will do some additional stuff based on that symmetric key, and they might drop the connection if they notice that the result is garbage because they didn't agree on the key in the first place, which is exactly what would happen if Bob would use his implicit rejection key. So in a sense, in bigger protocols, the implicitly rejecting CAM will revert to the explicitly rejecting one anyways, albeit with some delay. And for me, it's not clear how much security this delay would add. And then there's also the provable security perspective. I think one of the main reasons why the NIST proposals chose implicit rejection was that quantum security proofs were available for that much sooner. So for explicit rejection, in the at the beginning, we had to alter the encapsulation procedure by appending to the ciphertext an additional tag, which was another hash of the message, often called key confirmation hash. And this was kind of silly because it was just for proofs to go through. And it added some communication overhead, so that wasn't great. And then Zenrik came in 2019 and famously showed how we can essentially record quantum queries. That gave us much better tools for security proofs, and we could drop this additional key confirmation hash. Yeah, so as follow-up to Zandri's result, we got the first security proof for the standard FO transformation with explicit rejection, but the proof still was highly less tight than the implicit counterpart. And this gap between implicit and explicit left some additional room to worry. So this is why in 22, we wrote yet another paper that pushed the bounds closer to the implicit rejection bounds with two limitations. The first limitation is that the result only applies to probabilistic schemes because it crucially relies on some random oracle tricks that only work if you have a probabilistic scheme and tie the encryption randomness or noise to the message using another hash function, which you can then model as a random oracle. And maybe the more interesting limitation is that we had to require some correctness properties that proved somewhat unwieldy. So when we're talking about correctness errors, I already mentioned for lattice and code-based schemes, it sometimes happens that encrypting and then decrypting will not lead you to the original message. And this is not just a matter of functionality, it's actually a matter of security because it has been shown that if you are able to craft enough failing ciphertexts, you can reconstruct some information about the secret key, so not great. This was already captured in the security proofs in the 2017 paper. And the way we dealt with that was to upper bound the per message failure probability by a bound we call delta. This is also sometimes called delta correctness or worst case correctness. And the definition was quite conservative, which made it nicely integrating into the security proofs. But on the other hand, it doesn't play nicely with how this delta term is estimated by scripts in practice. So this part of the proof will then become a heuristic. Yeah, this is why in the paper on explicit rejection, we decided to deal with correctness errors a bit differently. So if we look at the bound, there are three terms. The first term is basically key indistinguishability if the attacker wouldn't be allowed to post decapsulation queries in the first place. In the second and the third term bound the amount of information you get from decapsulation queries. The third term is a term that's not as interesting for this paper, but I still wanted to mention that it is important because it poses some limitations on the public key encryption scheme. So basically this term means we need to have enough entropy in the ciphertexts or in the encryption procedure. The more interesting term is in the middle. This deals with correctness errors. So we bounded the amount of information by a computational game in which the attacker has to find decryption failures. However, this definition was given in an extended version of the quantum accessible random oracle model. And it also, it's a bit unwieldy. Let's say it's a bit unwieldy. So it will give scheme designers some headaches if they want to find a nice upper bound. This is why we broke it down further into some simpler to analyze terms, but even those were not like super easy to analyze for people who just want to design a scheme. So to sum this up, you can get more fine-grained bounds, but only if you are willing to do additional analytical work. So the question that motivated this work was if we can replace this computational notion with a delta heuristic with which scheme designers might already be happy. And luckily the answer is in the affirmative. So we can bound this problematic term in the middle by a typical Grover search bound defined relative to worst case correctness. This is a quite typical term. If you are familiar with FO bounds, and in a way you get the best of both worlds. Now you have a proof for explicit rejection and it works for the delta heuristic. I will only say a little bit about the proof. So the first step is to relate this failure CCA game, this computational notion, to a search problem in which the attacker is tasked with searching for a message that will fail to decrypt, having the public key and the secret key, access to the random oracle that ties the message to the randomness, modeled as a compressed oracle, and an additional extraction interface that will give the attacker pre-images of ciphertexts. So the attacker will query the extraction interface on a ciphertext. The interface performs some measurements on the Oracle database, then puts out a message that encrypts to the ciphertext. And for people who are familiar with search bounds, this looks a lot like a search problem. So it might be quite intuitive that we get a Grover search bound. The only thing that's hindering our reasoning is that we have this additional interface performing measurements on the database. So the second step of our proof is to show that this additional extraction interface doesn't mess up our reasoning, essentially. Yeah, so to do so, we give a lemma that's essentially it's a quantum counterpart to a hybrid argument for search problems. So intuitively, this says we can bound the probability of the attacker finding a failing message in the end by the probability that its ith query would have triggered a decryption failure. And if we maximize over that, we are exactly at delta, so we can simplify the sum quite a bit, square both sides, and get our nice Grover bound. Okay, so to wrap up, we show that the bounds for explicit rejection, FO, are not far from the known bounds for implicit rejection. And to do so, we revisited this extended quantum random oracle model framework that is very useful to further our almost classical reasoning, and showed that this extension doesn't disturb oracle search bounds. And for details, I invite you to look at the full paper. Thank you.
Thank you very much for this lovely talk. Are there any questions? Yes.
Hi, thanks for the lovely talk. You mentioned several times a delta heuristic. So in HHK 17, it's just a formal definition. What do you mean when you say delta heuristic?
About the heuristic?
Yes.
So I'm not perfectly sure how the scripts are written in practice,
Actually.
right? So the delta definition, it's just a statistical definition, right? You're taking the expectation over key generation, then you're maximizing over the message and taking the probability.
Mm-hmm.
And for the estimator scripts, I think people exploited the LWE assumption to reason that some of the terms you need to estimate can be replaced by something completely random.
Oh, I see. So it's scheme designers using a heuristic. I see.
Yeah, so in a sense, this boils down to the heuristic assuming that an attacker doesn't have the secret key, right?
And maybe just another short question. Your subtitle is completing the picture.
Sorry?
Your subtitle for this talk is completing the picture. Can we
Yeah.
now expect no more papers on the FO transform? Or?
I can't promise you that we don't see any more papers on FO. So I think a lot of people will still be working, for example, on the quantum random oracle model tools to argue about this first term in the sum, the passive security of the key, because we need better QROM tools to do the random oracle model reasoning. So for people who are familiar, we are talking about one way to hiding. We need to tighten this up because the optimal bounds are still not determined. So I think there's more to be expected.
Brilliant. Thank you.
Thank you for the question. Are there other questions? Okay, so let's thank Catherine for her excellent talk. Thank you very much.